Hello and welcome to this video on p-hacking and why it is a problem. In research, there exist many solutions, but these solutions are hidden behind problems, puzzles, and tricks. To get to the solutions and sift out the false promises from real answers, we use statistics. This is where and how p-hacking is a problem. To understand what this is, and particularly what p-hacking is as a problem, we must first work through 3 points. The simple reality that correlation does not equal causation, statistical significance, and then type 1 and type 2 errors. This will help to understand not just what p-hacking is, but why it is a problem. Let's start with a relatively simple thought experiment. Think of the students in your class at high school. The chances are good that you had a reasonably even split between males and females. And now apply this to your university or technical school education if you studied further. Finally, the people in your workplace. If you were to look at each stage of your studies or education and employment, you would likely see something along the lines of an equal distribution of males and females in high school. And depending on your sex, your further studies would be even more divided and skewed, and particularly depending on what it is you studied. And then finally, in your current workplace, it should be the most skewed. This creates a correlation with your particular sex and how many of your fellow gender are present, not only in many degrees but occupations. These will generally have at least somewhat subtle division by sex, if not a very clear division. That is more of one gender than the other. For example, more males as lawyers and politicians than there are females who tend to take on roles like nursing and childcare. The problem here is that just because there is an association between sex and study, occupation, and so on, that does not mean there is a causation necessarily. We regularly make light of this with the website Spurious Correlations. To know if you have a line of investigation worth chasing, you need to use statistics to understand if what you're looking at is actually explained by just the variables that you're putting forward. For example, the sex and the choice of what you study or the occupation you pursue. This brings us to significance. If your sample is statistically different from another, you can say to some degree that yes, there is more than just correlation. And this will bring us to p-values. P-values are a number that tells you how much of the answer is not explained by your model or your proposed variables. This value is typically set at 0.05, or more accurately an alpha of 0.05. That means if your result is less than the alpha, or p-value less than the alpha, the results are much more likely to be explained by your answer or your variables than they are by something else. For example, if we were to test car brands and age, if you received an alpha of 0.05, it would be significant, and therefore there would be certain brands more appealing to certain age groups. For example, a Ferrari or a Porsche and those over 40. If instead the p-value was at 0.06, it would not be significant, and anything below the alpha would also not be significant. While 0.05 is the typical, or let's say a default standard, there are more stringent designs, and these can require an alpha of 0.01 or 99%, and some are even more stringent again. In comparison, there are very liberal or low-quality studies that can have an alpha of 0.1 or up to 10% of the explanation can be missed. This is typically not considered a good sign if you're looking at a publication and their alpha is set so low. In summary of this part, if your p-value is at or below your alpha, you reject your null hypothesis, or more easily put, your theory that you've been testing is correct. On the other hand, if your p-value is greater than the alpha value, you accept your null hypothesis, or that your theory is wrong, or close enough to in both cases. To get your p-value or significance, you will need to run statistical tests. Now, they could be t-tests, ANOVA, or anything else that's appropriate to what you're doing, and there are ways to figure this out. In the end, though, they all produce either a p-value or an equivalent value that you use to decide whether or not you should reject your null hypothesis or accept it. This brings us to type 1 and type 2 errors. In short, these are where your statistical test will still get the wrong answer, even if your results, according to the statistics, are significant. A type 1 error is a false positive. Think of a pregnancy test if you will. It's a pregnancy test telling you that you're pregnant even if you're not. A type 2 error or a false negative is when you have the exact opposite problem. That is, for example, you are pregnant but the test says you're not. These two scenarios are often explained with the analogy of criminal convictions rather than pregnancy. A type 1 error is where an innocent person is convicted by a jury. That is, although they were presented with the data that shows that they're innocent, they were still found to be guilty. A type 2 error is where a very good lawyer has been able to twist the data or evidence and present it to the jury in such a way that they find a guilty person is actually innocent, although at that point they're no longer a guilty person. And now that we've been over the three major concepts that underlay p-hacking, we need to get to the substance of this video. When you first set up a study, you will find some sort of correlation, typically speaking. At the outset, you may not know that the correlation is unrelated to the causation, so you obviously will need to go on to statistical tests, and this is all fine, because you're basically trying to figure out if what I have found is actually correlated, and if it's correlated, is the causation a thing that I should be looking at as being warranted. The further studies don't exactly worry anyone if there is that causation. After all, even if you find that it's not significant, you may still have causation and it gives you a line of investigation, somewhere to look at to figure out, if my variable is not responsible, what else can I look at? The problem with p-hacking is the people who engage in this generally jump straight into step 2. They don't look at correlation. They start running statistical tests on every variable that they have data for, and this is the problem. What they'll do is they'll keep running statistical tests on everything until something starts to show statistical significance. It's the scientific version of throwing off shit against the wall and see what sticks. Once you have the statistical significance, then they go back to see if there's correlation. If there is, and in some cases even if there's not, the association or correlation, they still claim that there's something there because statistics says so. This brings us to the problem of type 1 and type 2 errors. This is something that p-hacking is especially prone to. Because you have no real guideposts or indicators that what you found is true or not true, you don't know if the associations you found are accurate. For example, spurious correlations are an example of this. If you found cheese and math doctorates are related and found statistical significance, there may not actually be a relationship. This would be a type 1 error. And by contrast, you might have a variable that contributes to your findings, such as socioeconomics, diet, genetics, and more that get rejected because the p-value is too low and therefore you committed a type 2 error. And this is the problem with p-hacking in research. It is not directed searches. There is no true underlying reason for the tests. You're just trying to see if something has significance. And that doesn't really work because you've taken it out of the context needed to figure out whether or not it's actually correct. This leads to studies making all sorts of unfounded claims of significance. A very good example recently is that which associated glyphosate and fertility in France, the problem being that all of the individuals who were involved were having fertility issues, and this is an exact case of type 1 error. They found an association and a significance where they shouldn't have. In other cases, it can ignore significant variables, using the simple example of criminals who get away with a crime. The concepts are a bit confusing in some ways. Overall, as long as you understand these two rubrics, you can understand what it is you're trying to achieve, and that's error types and p-values. It can be simply put as, if you find significance but reject the hypothesis, and if you don't find significance but accept the null hypothesis, depending on whether or not you've approached this in a way where you can be able to say with some confidence that actually, I know that this is related because I can show you the relationship, rather than just, I've done the p-hacking, which is generally done first, and then gone to find relationships. Most people go in the sequence of some sort of correlation, statistical testing to see if it is significant, followed up by whether or not they've committed a type 1 or type 2 error, and this is done by checking in other ways. This is p-hacking in a nutshell, a cause of spurious findings that taint the literature with lines of investigation that were almost randomly generated and now waste time, effort, money, and specialization of people chasing things that were never going to work out if the research had been done right in the first place. But unfortunately, in the environment of publish or perish, p-hacking is just too common. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please do post any comments, questions, or suggestions you have below.